All right. So how's it going?
Going good.
Good. It's Friday. Any questions? I don't remember what we were doing Wednesday. What were we doing?
We were talking about the ciphers, like.
Oh, yeah, we started talking about ciphers. Okay. Someone took that down, so I put it in the hallway out there. So it's Tuesday or Wednesday, and I think it's either 12 to 1 or 1 to 2. But those flyers should be floating around. If you don't see one, I'll find one for you. So there's no school on Monday, so we miss Monday. And then Friday is your midterm, so Wednesday, among other things, we'll spend some time reviewing for the midterm, not the final, for the midterm. But it's basically going to be everything we've done up to this point. So today we're going to talk about crypto, and most of what we're going to talk about you're not going to be responsible for the details of, okay? Just sort of the general ideas. And then towards the end of today, we might start talking about the next unit, which is mathematical induction. And there will be no mathematical induction on the midterm, okay? So once we're done with crypto, everything else is sort of off limits for the midterm. But what we've done up to this point, so sets and set theory, operations on sets, the proofs that we've done, even odd numbers, equivalence of logical expressions, identities, De Morgan's theorem, those kinds of things, and fallacies and quantifiers and all that stuff is fair game, and the number theory stuff we've been talking about, including stuff related to modulo numbers, systems, and so on, is all fair game for the midterm. So we can talk more about it next Wednesday, but
And we get 4 pages of notes?
yeah, you get 4 double-sided or 8 single-sided pages of notes. I don't think you need nearly that many, but I didn't want notes to be a limiting factor. However, historically, if I say open book, a number of people will not study because they got the book with them, right? And so I'll say, use Fermat's little theorem to find this expression modulo this thing. And so they'll say, okay, Fermat's little theorem, and they'll look it up in their book and they'll start reading it. They've never actually done anything with it, right? So it's really just to kind of keep you from turning the midterm into a mad dash through the book, which is hundreds of pages. But I don't think 8 pages is going to be a limiting factor for you. There should be plenty. That doesn't mean you need 8 pages. So let's talk about cryptography and crypto systems, and we sort of talked a little bit around what the motivating idea is for being able to do cryptography, which is this idea that communications are inherently insecure. Even today, right, anything that you transmit can be intercepted with a $10 radio, right? There's no secure communication. Fiber optic starts to get a little better, but if there's any weak spot along the transmission line, you can fiber optic to this place over here, but if they send something in an unsecure link, your transmissions are exposed. So we really don't rely on security of transmissions in that nobody can eavesdrop. We assume people can eavesdrop. We assume people can intercept our transmission and inject their own information into it. Right, so person in the middle attack, these things are just realities, right? When I send an email to somebody, it's going to bounce through several different machines along the way from here to there. I don't know anything about those machines. I don't know who's operating them. I don't know what their agendas are, right? So we need to inject security at the content level rather than the transmission level. We have to assume somebody might intercept this, somebody might try to replace it with something else, but we try to make the message itself as secure as possible so that when someone sees our message, they can't understand it. When somebody tries to fabricate some piece of our message that didn't come from us, the recipient can say, hey, this is not authentic, this has been tampered with, right? So that's the level of at which we try to have security in our communications. So cryptography is largely about this question of preventing others from reading a message and being able to validate whether a message is authentic. So we talked about Caesar ciphers, which is basically you want to send a message like hello. And we have a secret encryption, which is like add 3 to each letter, so that's our encryption. And so instead of sending HELLO, we send the following. Right, which sounds like a Norwegian beer maybe, I don't know. So you get this message, and the recipient gets this, and they know that it was encrypted by adding 3, so to decrypt, they subtract 3. And they'll bring down 3 from each letter, and they'll get back the original text. So plain text, cipher text, plain text. Okay, encryption is turning plain text into cipher. Decryption is turning cipher text back into plain. And the fact that we encrypt by adding 3 and we decrypt by adding -3 should catch your attention. This is what we call a symmetric cipher. If you know how to encrypt, you know how to decrypt, and vice versa. So Caesar ciphers are not terribly secure. Right? For one thing, there's only 26 possible keys you could use. So you could try each of those until you get to something that looks like not gibberish. But even if you make it more sophisticated, even if you take blocks of letters and you start adding larger numbers to them to shift, the text you're sending is not random. If the text you're sending is English, we can do a frequency analysis. Because, for example, we know the letter E is the most common letter in the English language. So if you shift your letters and we suddenly find the letter Q is the most common letter in these encrypted messages, we can deduce that the letter Q might be the same as the letter E. And you find how far that distance is, and you postulate that's your encryption key. You try to decrypt using that, and there's a good chance you're going to get back plain text. So these are not terribly secure, but it's a good example of a cipher, and in particular a symmetric cipher. So a better version of this is a transposition cipher. And so picture some small set of integers, and I'll just pick on 4 integers. And this is not a set because I'm paying attention to the order of these things, so it's like a 4-tuple. And I'm going to define my encryption as follows. I'm going to take the first of 4 letters, and I'm going to put that in position 3. And the second of 4 letters, I'm going to put in position 1. And the third of 4 letters, I'm going to put in position 4. And the fourth of 4 letters, I'm going to put in position 2. So I'm going to take my text, this is a test, and I'm going to break it up into chunks of 4 letters. And I'm just going to pad some spaces at the end here. So I have a nice number of blocks. And now my first letter I'm going to put in position 3, my second letter in position 1, my third letter in position 4, and my fourth letter in position 2. And I'm just going to rearrange everything within these blocks accordingly. And I'm most likely going to make some mistakes here, but you get the idea. And so we send this gibberish looking message. A/T/I, I blank blank S, and so on and so forth. So this is our encryption. Well, how do we decrypt? We decrypt like this. So we take the third letter, we put that in position 1. We take the first letter, we put that in position 2. Take the fourth letter, put that in position 3. Take the second letter, put that in position 4. And we can get back our original text. And so this is our decryption key. And again, it's symmetric. Right? If you know how to decrypt, you know how to encrypt, and vice versa. So it's a symmetric cipher. And it's a little more secure than just a straight shift cipher. But there's other ways to attack this. You could look at frequency of words. And we know certain words will occur again and again. For example, the word the will occur again and again and again. And we might find a particular pattern of 3 letters in certain positions, not necessarily consecutive, occurring again and again and again. And they contain the letters T, H, and E. And we could postulate that's probably the word the. And we can start to piece together what this transposition might be. So it's not very secure, but it's a little better than shifting. Anybody ever have a decoder ring when they were a kid? Cool. Used to get them in cereal boxes, and it was basically a Caesar cipher. It had a little copy of the alphabet on an inner ring and a copy of the alphabet on the outer ring, and when you turn the outer ring a certain number of clicks, it would effectively turn letters into other letters. And then you could use the same thing to decrypt. You didn't even have to move the dial. All right, so this is the way encryption was done for a long time, right? And encryption methods got more and more sophisticated and were based on more complex operations that made it harder to just look at the encrypted text and figure out what the decryption or encryption algorithm is. But they all had this property of being symmetric. If you knew how to code a message, you automatically knew how to decode it. Because the decoding was basically something that undid the coding, right? And if you know how it's coded, you can figure out how to reverse that, and that tells you how to decode it. So that was encryption for hundreds of years. And there's a problem with that. It wasn't a problem at the time, but it would be a big problem today if all of our ciphers were symmetric like this. Because anytime that you go online and you try to buy something and you want to send a credit card, what happens? Well, you can't send your credit card number in plain text because communications aren't secure. So you have to encrypt it somehow. Well, suppose you're ordering something from Amazon and they say, okay, when you send us your credit card number, we want you to add 3 to each digit, okay, to keep it secure. Well, anybody who is going to send something to Amazon knows I'm going to add 3 to each digit. So if I put up my radio and I listen to your credit card number go across and I know you're encrypting it for Amazon, you've added 3 to each digit, I can subtract 3, I got your credit card number, right? And Amazon can't come to each of us and say, okay, you're going to add 3 and you're going to add 17 and you're going to add 112, right? They want everybody to have the same encryption key so that you don't need to do something, meet in a back alley somewhere and get a secret password from them. You can just hop on and you can start ordering stuff. But since everybody knows how to encrypt, if it's a symmetric cipher, everybody knows how to decrypt. So e-commerce does not work with symmetric ciphers, right? Anything where everybody needs to encrypt, wireless communication, right? Our routers all know how to encrypt in a certain way. That doesn't work. So, enter these people. Can you tell it was the 70s? So this is Ralph Merkle on the left. I met him in the 90s. He was working for a company called Zyvex, forefront of nanotechnology. Really interesting character. Person in the middle is Martin Hellman from Stanford, and the person on the right is Whitfield Diffie. So Martin Hellman, he was at Stanford, and he had this idea of being able to use computers to do things like order pizza, right, and give a credit card number and pay for it, but have it be secure. And so he had this vision of an asymmetric cipher, some way that you can have one key to encrypt, so everybody can code up their information and send it with the same key, but a different key for decrypting that could not be predicted from the encryption key. So an asymmetric cipher. You know how to code a message, but you do not know how to decode it. And he saw the possibility of using this in electronic transactions, which he thought was inevitable. He thought this was coming. This was in the 70s. And he was told that's impossible, right? If you know how to encode, you're going to know how to decode. It's you know, it's the only way. There's no other possibility. Sorry, this was in the 60s. But he wanted to develop this technique anyway, so he was thinking about this. So Whitfield Diffie, on the right, got his bachelor's in mathematics from MIT in '65, and he started traveling around the country talking to researchers in cryptography. And he was just interested in what was going on. And he got to IBM at one point, and he was talking to these people, and they said, you know, you should go talk to this guy named Hellman. I think you two might have a lot in common. So we got a hold of Hellman's contact information, and he made an appointment to come by one afternoon for 30 minutes to talk to this person. And he knocked on the door, and he introduced themselves, and they started talking, and they talked, and they talked, and they talked, and it got to be dinner time, and they made dinner, and they ate dinner together, and they talked, and it got to be about midnight before he left. And it was this like instant bond, right? Because they had been both kind of then searching for this idea of an asymmetric key, and so they had a lot in common. So they started collaborating, Martin and Diffie, Hellman and Diffie. So Ralph Merkle was an undergrad at Berkeley at the time, and he was taking a computer science course in security, and they had to do a term project in their course, and he was trying to come up with a cool project, and he thought it would be cool to come up with a way to implement an asymmetric cipher. So he put together a proposal, and he gave it to his teacher, and the teacher said, you know, this is muddled terribly, were the exact words. And he rejected his proposal. And so like any good computer science student, he dropped the class. And he said, forget that, I'm just going to spend my time working on this project because I think this is really cool. So he started working on this, and he got some code written. So he finished his bachelor's. He was working on his master's degree at Berkeley, and he was talking to people about this stuff, and somebody said, you know what, there's a couple of guys up at Stanford who sound just like you. So he went up to Stanford, and he started snooping around, and he found these two people, and he became Hellman's doctoral student. So he started working on a PhD. So later that year, in 1976, they had an algorithm together, and Hellman published it, and Merkle and Diffie, their names were on the paper as well because they contributed, but it was Hellman's paper. And one of the colleagues at Stanford got worried about this and said, you know, they're talking about an uncrackable code here. They're talking about a way that people can send information secretly and the government can't figure out what they're saying. And so the colleague called NSA. Everybody know what NSA is? No such agency. They're up at Fort Meade in Maryland, National Security Agency. So NSA got interested in the work that Hellman and company were doing out here. And they said, well, what do we do with this? Right? This algorithm, if this gets out there, this is going to change the whole playing field. So they classified it as a munition, okay, as a weapon of war. This was a mathematical formula, right? It was an algorithm, and they said this is a munition, instrument of war. So you write a paper on some new results. What do? You publish it, and you go and you present it at a conference, right? So they plan to present this at a conference in October 1977, and government said, you can't do that, this is a secret. And they said, this is mathematics, right? There are no secrets here. And they said, if you go to that conference and you present these results, you're going to be arrested. So they talked to the attorneys at Stanford, and Stanford basically said, if you're arrested, we will pay for your legal defense. Okay? If you're found guilty, we will not go to jail for you. Okay? You're going to have to go to jail. And we can't legally pay any fines that might be levied against you. Right? But we'll stay with you up to that point. And his two students were advised, don't do this. Right? Why? Well, Hellman had tenure, right? So he was a tenured professor, so he had a good measure of job security. He was established in the field. He had a reputation. A few years in jail probably wouldn't be the end, especially for this. But a student who's fresh out of school, don't really want to start your career with a jail term or worse. So students were told not to talk. But they decided they wanted to talk anyway, until they brought it up to their families, and their families talked them out of it and said, we don't really want you to go to jail. So they went to Cornell to present this paper, and Hellman went on stage to do the presentation. The students were on stage, but they were off to the side. And nobody knew what was going to happen, right? They didn't know if these people were going to be arrested, or agents going to storm the stage, things like that. Turned out nothing happened. They gave their talk, and no arrests were made, and that was it, right? Once this had been presented, it was out there in the public, and that was the end of the government monopoly on encryption, because now anybody had access to this technique to do extremely secure encryption in this way that was asymmetric. So that was 1977, and later that year, these three people, so this is Ronald Rivest, Adi Shamir, and Leonard Adelman, that's RSA. So RSA Encryption, which you've probably heard of, that's the R, the S, and the A. And they improved on the work of Hellman and commercialized this. And so now, of course, this stuff is everywhere, and it's all in the public domain. Anybody remember Netscape? So when Netscape came out, right, that was an early, I guess technically it was a browser. That was an early way to get online. And it had encryption, but it had two versions of encryption. If you were in the US, you could get the good version. But if you weren't in the US, you could get the not so good version. And it was different levels of encryption. One was doing 40 bits and the other was doing like 128 bits or something like that. And if you got the good version in the US, you had to agree in those user agreements that you wouldn't export it, you wouldn't use it outside the borders of the US, you wouldn't send a copy of it to anybody outside the US, all this crazy stuff, right? Because the US wanted to make sure that if you were outside of the borders, you used weaker encryption than you used in the US, because they knew how to break 40-bit or whatever it was encryption, but not the stronger one. So this is all history at this point, but it wasn't that long ago that people got really worked up over these things. I remember reading about an editor at a technical magazine wanted to try to bring an encrypting cell phone onto an airplane because it was classified as munition. And so, he was bored, I guess. So he basically went through security with his phone and told people, this is a weapon. Can I bring it on board? And, got security over there and all people upset and stuff like that. It wasn't that long ago. So in some ways we're in a much better place now. All right, so how does this work? I'll give you a run through of the basic algorithm for RSA, okay? And the details will be a little sketchy and the feeling at the end will not be terribly inspired, but it uses a lot of the stuff that we've been doing in this unit, okay, talking about number theory. I just want to kind of present it as an application of of some of these concepts. But you can actually work through this with like a simple example and encrypt a small message and decrypt it on the other side and so on. But let's see why this works. So it's based on prime numbers. And the basic idea is that if you have two very large prime numbers, it's really, really easy to multiply them, right? If you've got a computer, you just, pencil and paper, column by column, multiply, add together. We know how to do that. There's no trick to that. But if you have just that large product, it's really hard to figure out what the two prime numbers were that multiplied to give that. Right? So if you have two primes, you can multiply them very easily. If all you have is the product of two primes, it's very hard to figure out what the primes are. Okay, that's where the asymmetry is going to come in. So here's the basic setup. You start off with two primes, P and Q, and they got to be large. Right, thousands of digits, whatever. So pick P and Q to be large primes and set n equal to their product. And then pick some large E such that the greatest common divisor of E and P minus 1 times Q minus 1 is equal to 1. So when the GCD of two things is 1, we say those two things are relatively prime. So 5 and 14 are relatively prime because they have no factors in common. 35 and 100 are not relatively prime because they're both divisible by 5. But 35 and 101 are relatively prime. So P minus 1 and Q minus 1, multiply those together, pick some number that's relatively prime to those. And that's easy to do. And so our encryption key is a pair of numbers, N and E. So you tell anybody who wants to send you a secure message the value of N and the value of E. And the assumption is that even though they know N, they can't figure out what P and Q are. If they can, all bets are off. Then they can decrypt. But you give them this product and you give them something relatively prime to P minus 1, Q minus 1. All right, so let's suppose your message contains just uppercase letters, A through Z. And so we'll do a simple encoding. Where we have two digits associated with each letter, 0, 0, 0, 1, all the way up to 2, 5. And we break your text into n characters. So there's no spaces, there's just letters. So we break your text into n characters. And we choose n to be as big as possible such that the following is true. This number that we get by writing n 25s next to each other has got to be less than this part of the encryption key n. In other words, if you were to encrypt a bunch of z's, we make our block size big enough so that the number corresponding to that block is smaller than n. But we make it as big as possible. This is why we want big primes also. So you get a big block size. So you start off with a message, you convert your letters to these two-digit things, and the number that corresponds to that message is going to be smaller than n, basically. Okay, and it's a big integer. Okay, because n might be hundreds of digits, so you might have, 100 letters in your block, and you get some big 200-digit number that corresponds to that chunk of text. Okay, so here's something to take on faith. This is a theorem. If you know P and Q, you can find another integer d such that d times e is congruent to 1 modulo p minus 1 times q minus 1. We haven't talked about why this is, but it's true. In other words, we can find an inverse of this part of the encryption key E, as long as we know these primes. Okay, so we know P and Q, we can find some D that when you multiply by E is 1 more than a multiple of P minus 1 times Q minus 1. And this D is going to turn out to be how we decrypt our messages. We know E. E was a large number that was relatively prime to P minus 1, Q minus 1. So everybody knows E because N and E are part of the encryption key. But if you don't know P and Q, if all you know is E, there's no way to find this D. But if we created this encryption key, we know what P and Q are, we can find this D. And this D is going to be what we use to decrypt. Okay, so E is for encryption, D is for decryption. All right, so to encrypt a message, we take your message, this big long integer that's made up of these 2-digit things for each symbol. We take your message and we raise it to the power E, and we reduce it modulo n. That's your ciphertext. So you've got a 200-digit number, and we're raising it to some ridiculous power that's hundreds of digits modulo some other thing that's hundreds of digits. Modular exponentiation, Fermat's little theorem, right? All of these things are used to make this tractable inside a computer. You can do it by hand if you pick small primes. But for big primes, right, it's pretty easy for a computer to do it. So that's the encryption part of RSA, right? Set up these magic encryption key elements, N and E, choose what your block size is, take your message, write it out as a big integer, raise it to the power E, reduce it modulo N. You get another big integer, that's your encrypted message. The question is, how can we take this encrypted message C and get back our original message M, right? And there's no ETH root operation modulo N, okay? Which is why this is secure, because integers just do that. All right, so that's our ciphertext. How do we get back to our original message? So here's where it gets kind of weirder. But like I say, you're not going to be tested on these details. So since D times E is congruent to 1, modulo P minus 1 times Q minus 1, right, which was how we picked E, right, which we could find, that's how we picked D. So D times E is congruent to 1 modulo P minus 1 times Q minus 1. There exists some integer K such that DE equals 1 plus some integer times P minus 1 times Q minus 1. That's what it means to be congruent to 1. It's 1 more than a multiple of P minus 1, Q minus 1. So if we take our ciphertext and we raise it to the power D, well, our ciphertext is M raised to the E, so this is M raised to the E raised to the D. which is law of exponents m to the d times e. And we substitute d times e, so this is m to the quantity 1 plus k times p minus 1 times q minus 1. And this is all modulo n, right, because c is m to the e mod n. And remember, n is p times q. Well, if we have a congruence modulo p times q, we have the same congruence modulo p. Right? To say two things are congruent modulo p times q means their difference is divisible by p times q. And if it's divisible by p times q, it's also divisible by p, or by q. So we can write a pair of equations here, which is that c to the d is congruent to m times 1 plus k, p minus 1, q minus 1, modulo p. All right, assuming that m doesn't happen to be a multiple of p, and it's really unlikely that it is, okay, because m is just the number corresponding to your original message, and p is a really large prime number. So almost guaranteed m is not a multiple of p. And if it is, we can add something to the message to change that. P does not divide m, we can apply Fermat's little theorem. And Fermat's little theorem will say that m to the p minus 1 is congruent to 1 modulo p. So let's break this expression up. So c to the d is congruent to the following. M to the first is m. M to the k times p minus 1 times q minus 1. And I'm going to rearrange these things that I'm multiplying by and say this is m to the p minus 1 times k times q minus 1. And I'm going to use the law of exponents again and say this is m to the p minus 1, all raised to the k times q minus 1. And Fermat's little theorem tells us m to the p minus 1 is congruent to 1 mod p. So this is going to turn out to be congruent to m. Mod p. We can do the same thing modulo q. So we take our ciphertext, we raise it to the power d, right, the secret d that only we know, and we get a number congruent to m modulo p and congruent to m modulo q. Okay, there's one more theorem that we haven't talked about. It's called the Chinese remainder theorem. This was known thousands of years ago. And the Chinese remainder theorem is about solving simultaneous equations modulo stuff. So here we have an equation, c to the d is congruent to m modulo p, and c to the d is congruent to m modulo q. The Chinese remainder theorem tells us c to the d will be congruent to m modulo p times q. And since we originally picked our message so that whatever the letters are in our message, this number m is smaller than n, which is p times q. This is smaller than p times q, so m is just equal to c to the d. So by taking the ciphertext, raising it to the power d, we get back our original message, reducing mod pq. Okay, so why is this secure? It's secure only on the basis of the fact that we can't find this D, this inverse of E, unless we know what P and Q are. Right? So we tell the world N and E, and we keep to ourselves D. Anybody can encrypt their message by just taking their message, raising it to the power E, and reducing it modulo N. We can take that ciphertext, and if we know D, we can raise the ciphertext to that power, reduce modulo N, and get back our original message. So that's RSA in a nutshell. And like I said, I don't expect you to know these details. They don't leave me warm and fuzzy terribly. But it uses a bunch of the stuff we've been doing, right? Modular exponentiation, Fermat's level theorem, stuff like that. What I would like you to know is the difference between a symmetric and an asymmetric cipher. Okay, with symmetric ciphers, if you know how to encrypt, you know how to decrypt. Right? One is determinable from the other. With an asymmetric cipher, this is how you encrypt, this is how you decrypt, and knowing one doesn't tell you the other. Right? You got to know some other information to figure out the decryption key. That's the asymmetric version.
So if the prime number that we use is very, very large, how do we find that prime number if there's no set way of finding it?
You mine. So this is like Bitcoin mining.
You just guess and check, don't you?
You can guess and check, or you can look for things that are likely to produce prime numbers, like Mersenne primes, like 2 to a p minus 1. But you get a bunch of hardware, and you just start cranking through numbers. And so Bitcoin type currencies, right? When they first came out, they were built on similar principles. You needed to find really large prime numbers to be able to encode this stuff. And for a few years, people were mining Bitcoins, basically. They were plumbing the space of integers looking for large primes or numbers with similar characteristics. And after a while, the mine started to run dry. And it's gotten harder and harder to find these numbers. And so people started getting into things like FPGAs, right, field programmable logic, engineering 250, and building custom hardware that would just look for numbers with certain characteristics. About 3 years ago, a bunch of students, for their service learning project, they wanted to do Bitcoin mining. So they came up with software, they came up with hardware, different systems like that. It's a challenge. And it's one of the reasons why when we figure out how to factor numbers efficiently, everything changes, right? If you have a way to take a number n and say, oh, that's the product of these two primes, right? That instant, stop doing things online because there's suddenly no security. So this is why NSA gets really excited about things like quantum computing, right? So how many people know about quantum computing? Right, it's in the press every few months, and it's always the same. Somewhere in the first paragraph, it'll say practical applications in 5 years. Okay, I've been reading this for 30 years now. It's always 5 years away. Engineering 250, 270, right? We talk about computers, and they're built on the idea of bits. A bit is a 1 or a 0, right? And we can build up integers and characters and movies and all kinds of things out of a bunch of bits. Quantum computers are based on qubits, quantum bits, and a quantum bit is both a 1 and a 0. It's both things simultaneously. So if I have 8 qubits, that number simultaneously represents 256 different integers. 0, 1, 2, 3, all the way up through 255. And it's representing all of those things at the same time. So if I want to check to see if two numbers multiply to give me this number over here, I can take an 8-bit number of qubits and an 8-qubit number over here, and I can multiply them. And it's simultaneously multiplying all possible 8-bit numbers by 8-bit numbers. And my answer is, some weird nebulous cloud of 16 qubits that represents all possible products. And I just look for the qubit that corresponds to the thing I'm trying to factor, and I figure out what the two things were that multiply to that. So quantum computing is really weird, right? It's this idea of being able to do things in parallel, and it's based on loosely this quantum principle of superposition, right? The fact that certain things like certain properties of particles like spin. Your spin can be up or down, but in fact it can be both at the same time until you do what's called collapsing the wave function, until you observe it, and then it assumes one value or the other. But if nothing observes a quantum system, it exists in multiple states simultaneously. This is Schrodinger's cat, dead and alive, right? So it's a question of setting up the system in such a way that all the possible states are present, and then getting the wave functions to collapse precisely into your solution. And presumably, allegedly, we've been able to do this with small, like 5-bit systems, where people actually have, a few quantum bits, and they can exhibit this superposition. Now, this is a quantum bit surrounded by a room, 3 times this size, filled with equipment at about 0.1 degrees above absolute zero, right? So it's not something you're going to find in a laptop anytime soon. But there are places that are starting to sell time on quantum computers, or give away time on quantum computers. Actually, IBM is offering an interface to one of their quantum computers. And when we get to that point, all the stuff goes out the window because you can factor really quickly. So NSA gets really excited about quantum computing.
Wouldn't they not like it for the same reason they didn't like this?
Oh yeah. I mean, it's good because you can crack everybody else's messages, right? But everybody can crack your messages too.
So it's good until everyone else gets to
Yeah,
that point.
yeah, right.
Well, I mean, I guess you could try to use quantum computing to make your own asynchronous layer or something.
Yeah.
Because from there you can essentially make your own asynchronous thing and hope it works.
Right, right.
Make a different asynchronous.
And usually the way these things work is so how many people know what Enigma was? Right, so Enigma was an encryption system the Germans had in World War II. Very, very clever machine that you could type in a message and it would print out an encrypted version of it. And the password was set by setting the position of a bunch of disks. And every morning they would change the disks around to a new password. So you had 24 hours to figure out what the password was, and then you could start reading those days' messages, but the next morning, the password would change. And so a number of mathematicians were assembled at a lab in England to try to figure out how to crack this code. And they ended up inventing what was eventually called a Turing machine or a computer, right? Mechanical systems to run these calculations fast enough that they could actually figure out the password in a reasonable amount of time, a few hours. But one of the things they discovered was that they'd get a message saying the Germans were planning to torpedo this submarine at this location at this time, and they wanted to warn the people on the sub, and it's like, well, we can't do that because if we start warning everybody who's about to be attacked, the Germans are going to figure out we've cracked the code, and they're going to use a different system, right? So I would guess if you were a government and you had access to a quantum computer, you probably wouldn't tell people about it. You'd secretly read other people's messages, but you wouldn't act on that in most cases. And you would hope that nobody knew that you could do this. So, and who knows where the heck we are in reality. So, but this is a fascinating area of mathematics to me. If you're interested, look at elliptic curve cryptography. It's kind of cutting edge. And actually just found a really good introductory level text on it. It gets you into the stuff without any background other than algebra. So yeah, so that's crypto and quantum. All right, so questions, comments. All right, so let me start the next unit because we got time here and we're not going to have class Monday. Yes?
Just for others to remember the difference between an asymmetric cipher and a symmetric cipher.
Yeah. I think that's the most important takeaway.
Okay.
Say again?
You know how your presentation, or decrypting or anything asymmetrically.
Mm-hmm.
So maybe they didn't get arrested because by the time the government are the other way.
I don't know. It's a good question. It's a hot topic right now, right? I mean, it's in the news every few weeks. The government wants backdoors into some of these encryption methods, and the mathematicians are trying to explain to them there's no such thing as, you know, putting a backdoor in that only good people have access to, right? If you weaken the encryption system, you've weakened the encryption system, period. It's not like you can weaken it in a way that only some people can take advantage of it, right? That's not how math works. But we see this all the time.
There's the cases, the government in San Bernardino,
Yeah.
tillers of Apple, and
Yeah.
Apple didn't want to tell them how to unlock it.
Yeah, and then some random security agency supposedly did it in like 40 minutes.
Yeah, yeah.
Yeah.
Or maybe Apple finally did it.
Maybe.
For a big sum of money.
If there's only, or if we don't have a way to determine or to calculate infinite amount of prime numbers, so that would mean that our computers to this point would only have been able to calculate so many prime numbers, and I assume all of them would be recorded. So what if you just run an algorithm that uses only prime numbers to factor this number?
Well, we haven't found consecutive primes though. If you look at the largest known primes, there's big gaps between them, right? So we know some prime numbers with say 500,000 digits, but we don't know most of the primes up to that point. So most of the primes that we found, the record breakers, are things of the form 2 to a prime minus 1. So these Mersenne primes. But there's you know, large swaths of numbers that we just haven't explored. And if you think how many 100-digit prime numbers there might be, right? 10 to the 100th is a big number, right? There's 10 to the 38th particles in the universe, supposedly. Right, or sorry, 10 to the 72nd. 38 is 32-bit number. 10 to the 72nd, I think, particles in the universe, by some article I read somewhere. But it's not, you know, that big a number compared to some of these things that we talked about with like prime numbers and stuff. So yeah, it's definitely tricky. It's weird to think about. A lot of the security stuff is pretty bogus, right? Unless you're encrypting your phone, chances are your fingerprint scan, your face scan, all that stuff is really just window dressing. Because if you've got an SD card or some kind of memory inside the phone, if it's not encrypted, right, guarantee someone can rip the phone apart, go in physically with circuitry and start probing the circuit and read whatever they want, right? I can put a fingerprint scan on my laptop, but I can also stick in a flash drive, boot it up under Linux, mount the hard drive, and read it, right? So we can have these really fancy gates, but have like no fence attached on either side of it. And you can't get through the gate, you know, but you can walk to the side and just go through. And so there's a lot of that out there also. If you encrypt your phone, then you got a little better situation, but usually a performance hit too. All right, so let me start talking about mathematical induction. So I tell people I have two goals in CSE 215. The first is to give you some exposure to proofs, right? And not necessarily have you walk out of here as an expert in how to do proofs or even very comfortable doing proofs, but to have some experience with doing proofs, okay? And that's something that you'll encounter again and again. And when you write code, you're really kind of doing proofs in some way, right? When you convince yourself that if I do this and I set mid equal to high plus low minus 1 divided by 2, whatever, that this is going to solve this problem in some optimal way, right? You're kind of doing a proof at some level inside, convincing yourself that this algorithm works or that it has some sort of performance. So proofs are always in there. The other thing I want people to get out of 215 is mathematical induction. because mathematical induction is the key to understanding and be able to work with something we call recursion, which is a big part of what we do in CSE 222, recursive programming. And it's really just an algorithmic implementation of this principle of mathematical induction. But induction is such a powerful technique. We can do so many things with it that we already know how to do at some level, but we might not be able to formalize. And mathematical induction is a way to formalize these things that we already understand kind of intuitively. So we're going to spend at least a week playing with at least 2 weeks playing with induction, because we don't get a lot of time Wednesday and Friday's midterm. Midterm will be 50 minutes, so we'll have a little bit of lecture before or after. We'll be doing this for at least a couple of weeks. So we're going to talk about propositions, and we're usually going to talk about a family of propositions. So we'll write propositions like P sub n, P parentheses n, where n might be an integer, and let's say n is greater than or equal to 1. It could be bigger than or equal to 0, it could be bigger than or equal to 100, but for now, let's just suppose n is some integer that's positive, bigger than or equal to 1. And we're going to write a family of propositions, P parentheses n. So let Pn be the proposition, and it could be anything typically involving n. Proposition that if you play the stick picking game with n sticks, the computer can win if it gets to go first, or something like that. And we're going to want to prove, usually, prove that P of n is true for all n bigger than or equal to 1, where n is an integer. So our goal with mathematical induction is usually we have some family, some collection of propositions, and we want to prove that all of those propositions are true. So let me give you an example of such a proposition. Let P of n be the proposition that if we add n ones together, we end up with n. So P of 3 is the proposition 1 plus 1 plus 1 equals 3. P of 5 is the proposition 1 plus 1 plus 1 plus 1 plus 1 equals 5. P of 1 is just the proposition 1 equals 1. Now, do we believe that P of n is true for all positive integers n? Do we believe that if we add 1,000,000 ones together, we will get 1,000,000? We're all pretty confident of that, right? How do we know it's true? Have you ever added 1,000,000 ones on a calculator? I haven't.
Well, it's also part of the definition of what a million means. Like, what does it mean to be a million? Well, it's the definition, and so it's boiling down to the 1,000,000 ones added together. It's not directly that it means 1 times 10 to the 4th or whatever. 1 times 10 to the 6th. 0 times 10, blah, blah, blah. And it's just 1 times 10 to the 6th. What does 10 to the 6th mean?
So there's a belief that if we add
10 times 10 to the 6th times, which ends up, what does 10 times 10 mean?
So if we add something n times, we believe it's the same as multiplying it by n, right?
Yes.
And we know that if we do this with 2 things or 3 things, it's true because we know x plus x plus x equals 3x. That's a rule of algebra. But until you write out x plus x plus x plus 1,000,000 times, and somehow show that that's equal to 1,000,000x, how do we actually know that that's what's going to happen? Other than, you know, someone in a book said this works for all numbers. Yeah.
Prove that n1 is the same even or odd value as n.
Yeah, how do we prove that?
Could you go back for 1 million?
Go back?
Yeah, like, start at 1 million and
Oh.
everything.
Yeah, if you want to go through 1,000,000,
Well,
you can do that, right? But it's a fairly subtle thing to try to actually prove rigorously without somehow relying on words like obviously or clearly, even though it's obviously true.
So what if we prove 1 plus 1 plus 1 10 times it equals 10, and then 10 plus 10 equals 100
Okay,
that way, and basically kind of exponentiate.
so we could
away from
leapfrog like that. That would make it a little
For one
better.
thing, you can just keep going like that.
Yeah, in fact, if we did it, if we doubled the number of things each time, we could get there in 20 steps. Right, so what if we want to do a gazillion ones? Then we got to do a few more steps, we could get there. But this very general statement, if I just do n ones where n is any positive integer, I'm going to end up with n. How can we prove that's true without actually doing it for that particular value of n? This is what mathematical induction is about. Because we can see that this is true, we know that this is true, but we'd like to formalize it in a proof. So here's what we can do. We state that P of n is the proposition that adding n ones together gives us n. Okay, so we have to do two things. First, we have to prove that P of 1 is true. Well, P of 1 says 1 equals 1, and I'll let you take that as being true. I could force you to prove that too, but I won't. So P of 1 says 1 equals 1. We'll just say this is true. Therefore, P of 1 is true. Okay, this is what we call the base case. It's a starting point. The other thing we've got to do is the following. Prove if P of n is true, then P of n plus 1 is true. We're not proving P of n for every possible value of n. We're only doing one very particular thing. We're saying that if for some n P of n is true, we can show that P of n plus 1 is also true. Well, how do we do that? As usual, assume P of n is true, which means 1 plus 1 n times is equal to n. We don't know that that's true. We're just assuming that's true. And our goal is to prove that in this case, P of n plus 1 is also true. Well, if we do n plus 1 ones, that's equal to n ones plus 1 more, right? So adding n plus 1 ones is exactly the same as adding n ones and then adding 1 more. That's associativity. It says we can throw parentheses around here and we don't change our answer. Well, what is the sum of n ones equal to? We did it right here. We assumed P of n is true, which means that the sum of n ones is equal to n. And so the sum of n ones plus 1 is equal to n plus 1. And what have we just shown? If we take n plus 1 ones and we add them together, we get n plus 1. And that means P of n plus 1 is true. Now, by it themselves, we've only shown two things. We've shown P of 1 is true, and we've shown that if P of n is true, P of n plus 1 is also true. Mathematical induction lets us draw a conclusion from these two things. So by mathematical induction, P of n is now true for all n bigger than or equal to 1. Mathematical induction provides that kind of intuitive leap. Right? We know this is true because we know that if we add up n of these things, we're going to get n, and if we add one more, we're going to get n plus 1. And we can do that to show P of 5, P of 50, P of 5,000. Mathematical induction lets us generalize that and say, okay, it's actually true for all integers n bigger than 1. So let me give you the precise version of this. So here's one way to write mathematical induction. If we know P of 1 is true, and we know that P of n implies P of n plus 1, we can conclude P of n for all n. And this is like the coolest thing in the world, almost. Right, we have to show P of 1. We don't have to prove P of n. We just have to show that if we assume P of n, we can prove P of n plus 1. But we put those together, mathematical induction tells us, okay, P of n is true for all n. And I'm leaving off n bigger than 1 as an integer, that kind of stuff. But whatever your requirements are on n. All right, let me give you an application of this. We won't actually do the proof, but I'll show you the intuition of this. De Morgan's theorem. AB bar is the same as A bar or B bar. All right, that's good old De Morgan's theorem from 250. Do you believe this? A 3-variable version of De Morgan? Have you ever seen this? Democracy, how many people think it's true? How many think it's false? How many think it's like the devil and will destroy the universe? Let's try to prove this without doing too much work. And start with ABC bar. I'm going to group B and C together in parentheses. And now I have two things ANDed together with a bar on top. This thing and that thing. And so by De Morgan's theorem, this is the same as the first thing with a bar ORed with the second thing with a bar. That's just 2-variable De Morgan's theorem. And now I'm going to apply De Morgan's theorem again on this BC bar and say that's B bar or C bar. And we just proved our result. So this does work for 3 variables. Do you think it works for 4 variables? Do you think we can prove it? It's exactly the same proof. I've grouped my C and D together. My 3-variable version says this is the complement of the first thing A, ORed with the complement of the second thing B, ORed with the complement of the third thing C, D. And I'll just use plain old 2-variable De Morgan's on CD bar and write this as C bar or D bar. So pretty easy to show it for 4 things. Do you think it's true for 1,000,000 things? Do you want to watch me try to prove that? No. Right? To prove that, we're going to have to prove it for 999,999 things. And to prove that, we're going to have to prove it for the next number down. It's going to take 1,000,000 steps to work our way up to De Morgan's theorem on 1,000,000 variables. Mathematical induction, we can do this in a few lines. Right? All we have to do is show that if we know De Morgan's theorem works on n variables, it'll work on n plus 1. And that's exactly what we're doing when we go from 3-variable version to a 4-variable version. So all we've got to do is generalize how we get from here to here and phrase that in the language of if this is true for n, then it's true for n plus 1. That's called our inductive step, by the way. And then combine that with a base case like P of 2, which is our good old 2-variable De Morgan's. And then say, therefore, by the principle of mathematical induction, P of n for all n bigger than or equal to 2. So it's another one of these giant hammers you can just wave at things and say, by the principle of mathematical induction, and write down this glorious conclusion. And it'll come up again and again and again. Anytime that you can see how to get from one case to another, but you want to generalize it, there's a good chance you can throw mathematical induction in there. And we use this in programming also. Right? We write a for loop that takes a number n and does something for n variables, like a bubble sort. How do we know our bubble sort will work when we get to 1,017 variables? We haven't actually proven that, but we know if our bubble sort works for n variables, it'll work for n plus 1 variables. And we prove that it works for, say, n equals 1, our base case. We've got our inductive step, and then we use mathematical induction to say, okay, this algorithm works for all values of n, all sizes of data. So this will pop up again and again in computer science. All right, so that's kind of a preview of where we're going next, which is mathematical induction. I'm going to try to put together some videos. I have some videos already online that I'll link to that talk about some specific problems, but I'll try to do some videos that sort of go over this level of induction, and I'll post some homework questions. I'll probably get lazy and wait a few days to do that since we don't meet Monday, but I'll post them on Canvas once they're available. So your homework that was due Monday is due on Wednesday, okay? So you can turn that in then. And that was some number theory things, Fermat's little theorem and some GCDs. Other than that, I'll see you in 224 or have a good weekend. I'll let you out 5 minutes early.